Pilot 4 considers a Philips image-guided therapy system used for image guidance and support during minimally invasive treatment. Different multi-axis robot system configurations provide precise movement and positioning of the X-ray system in a complex healthcare environment working near humans. A challenging environment where novel technology can help to save more lives every day. The ambition within the IMOCO4.E project is to leverage emerging technologies of digital twin models, AI, and big data to accelerate new ideas to the market and enable the next step in predictive maintenance. Pilot 4 focuses on the geometry and motion of healthcare robotics and will collect data in all relevant system phases from development, factory, and field. To achieve this, we will need to extend data collection with high-rate motion data from layers 1 through 3. This data will be leveraged for digital twin and AI model creation in layer 4. A model-driven infrastructure is required to manage these new models, such that they can be leveraged in all layers and system phases and enable emerging technologies in the next generation of healthcare robotics. Let's have a closer look at Topic 1. Here we enable the development and integration of digital twin technology for real-time performance, accelerate commissioning, and the next step in predictive maintenance. To let a digital twin resemble its real-world counterpart, it is updated using data collected from its physical twin. Philips Healthcare already collects data from field systems and will extend this during IMOCO4.E with high-rate motion big data, containing many samples per second for over 50+ motion-relevant signals per motion axis of the robot, like set points, positions, and currents. This component has successfully been tested on development systems and is now ready for release to the field. Similar extension towards the factory is planned for next year. The new high-rate motion data has successfully been integrated in a data management system, and the high-rate motion data can be retrieved for the development and application of new digital twin and AI models from partners, like Philips Research developing new and improved predictive maintenance models. TUE developing of multi-rate parametric identification, which may be applied as input to digital twin and AI models. Reedon developing a digital twin model for robot collision detection based on a combination of data and Bayesian filtering. And UWB developing a data-driven adaptive method to correct for motion disturbances with the aim to reduce or even eliminate recurring motion calibrations. In Topic 2, we create the necessary toolchains and infrastructure to manage the models. The infrastructure automatically generates the different multi-axis robot configurations available in our portfolio by combining many component submodels. To manage the model complexity, we utilize generic reusable models, which are made configuration-specific by a parameter set. Based on a custom domain-specific language, the model is assembled from the many different Simulink and CAD component models in combination with the configuration-specific parameter set, resulting in an executable robot model which can, for instance, be used in the Simulink environment for testing and development, or actual deployment to target hardware. The DSL, parameter sets, component models, and accompanying tests are all maintained under version control and automatically tested as part of the developed CI/CD pipeline. This infrastructure now supports different levels of in-the-loop testing and thereby has an essential facilitating role in both Topic 1 and Topic 3. In the final topic, we focus on the challenging task of autonomous path planning and collision avoidance in a healthcare environment. To map the environment, we explored different sensor technologies installed on our robot, like radar technology from IMST and a vision-based system from Rexon, combined with recent advancements in localization and mapping algorithms like neuroradiance fields. The testing and training of these algorithms is currently performed based on virtual camera streams, which are generated from the robot models and virtual environment provided by the Topic 2 infrastructure. The same realistic robot models, virtual environment, and testing infrastructure allow for safe testing of the autonomous path planning and collision avoidance algorithms, considering the complex constraints of a mounted robot in a varying healthcare environment. The infrastructure is again leveraged to early validate the behavior of the path planning algorithms with the user by realization of hardware in the loop-like test environment. The setup allows for deployment of the novel algorithms on the robot model in a virtual environment, and the user receives a close-to-reality experience by use of virtual reality and enabling interaction with the robot by the physical control interface. This concludes the 2-year review status update on Pilot 4 Healthcare Robotics by cooperation with IMOCO4.E partners. Leveraging the deliverables of the different building blocks to achieve the set ambitions.